We have all seen swinging pendulums, bottles bopping up and down in a pond, or swinging springs, and other movements of these types. Hello, my name is Tom Atwater, and in this section we will discuss vibrating and oscillating phenomena known as simple harmonic motion. The periodic nature of the sine and cosine functions make them ideal for describing the motion of a point of an object that vibrates, oscillates, rotates, or is moved by wave action. Let's look at how the equations for a simple harmonic motion are generated. Here we have a circle, and we have an angle theta right here, and its corresponding point on the unit circle. And we have this length drawn out on the unit circle. And what we're interested in here is something called angular velocity. And we use the Greek letter omega, which looks somewhat like a curved W, as the letter to signify that. And what we're going to look at is letting theta, the angle theta, continue to move from its position to a new position based on the time, which of course we would use as t. And what it turns out is that the omega, which is the angular velocity, multiplied by t, normally in seconds, is going to be equal to the angle theta. So that's the relationship. Theta is equal to the angular velocity times t. What I want to do, though, is start back here at this point when theta is equal to 0 and point out that at this point, the x value is a, the y value is 0. But as we let theta move in this direction, which means that the point is moving in this direction, notice that what's happening is the value of x, which is signified by this particular point, the value of x is getting smaller and smaller. But at the same time, the y value, which we're signifying with the point Q, the y value of each of these points, right here, here, up to here, they're getting larger and larger until we get right to pi over 2 for theta. And at that point, what happens is the x value is at a minimum and the y value is actually at its maximum. Now, what happens as we continue along this circle in this direction? That is, theta is continuing to get larger and larger. Well, what happens is the y values of each of these points become smaller and smaller. The x values, which had been decreasing, are now getting larger and larger. As we move along the circle, we're going to see a repetition of what's happening, which is that as we move this direction and we look at each of these points along the circle, in this case, the x values are going back this way. The y values, of course, are growing in absolute value larger and larger until we get to this point where, again, the absolute value of this would reach its maximum. As we continue returning to our starting point, notice that what's going to happen to these values, the x values, which are the horizontal distances, of course, are getting larger and larger. The y values, however, are in absolute value getting smaller and smaller until we return to the point where the x value is at its maximum of a and the y value is at its minimum of 0. Now, what we're saying here then is that those points, the R point, which was the X value, the Q point, which was referring to the Y value, they are in the X value. Let's take the X first. The X started off at its maximum, and then it got smaller and smaller. Then it began to grow again in the negative direction, but then after we got to the pi value and started down the bottom of the circle, it started to return towards zero until it went to its maximum. In other words, the X value itself is oscillating back and forth. Similarly, the Y value, which started off at zero, it began to grow, then it began to come back towards zero, go beyond zero down to a negative value, and then when we started to return back up to a full circle, it returned. So it too was oscillating back and forth. Let's take a look at a picture that shows oscillating motion. Here's the graph, y equals sine of 1 over x, and we've only graphed it from -1 to +1. What I want you to notice is the graph is oscillating up and down between -1 and +1, which means the amplitude for this particular function, of course, is 1. You can see very clearly that this graph is oscillating back and forth, etc. And what I'd like to do is take you from this graph and show you what you would see if you did it on the calculator. So let's go to the calculator and plug in y equals sine 1 over x. So I take my y key, I plug in sine 1 divided by x, and then I want to look at my window, and in this case I'm setting my window at -1 to 1 for the x value, and -1.5 to 1.5 for the y value, and then I'll hit graph, and you can see it get drawn for you. So again, it shows the oscillating motion that we're interested in observing. So now, let's look at the formal definition of simple harmonic motion. Simple harmonic motion, the position of a point oscillating about an equilibrium position at time t is modeled by either S of t equals a cosine of omega t, or S of t equals a sine omega t, where a and omega are constants, with omega being positive. The amplitude of the motion is the absolute value of a. The period is 2 pi divided by omega, and the frequency is defined to be the reciprocal of the period, that is, omega over 2 pi. Realize that S of t is the distance of a single point which is in simple harmonic motion from its equilibrium point at whatever time t is determined. So let's take a look at an example where we use this. Suppose that a weight on a spring has initial position s of 0 and period p. Find a function s given s of t equals a cosine omega t. Evaluate s of 1. Is the weight moving upward, downward, or neither when t is equal to 1? Given that s of 0 equals -3 inches and p, the period, is equal to 8/10 of a second. So the equation that they've given us is s of t equals a times cosine omega t. S of t equals a times cosine omega t. In particular, when the object is released, which is t equals 0, the distance is 3 units below equilibrium, which means that s of 0 equals -3. then cosine omega 0. Well, omega times 0 is going to be 0, so cosine of 0 is 1, so S of 0 equals negative 3. What that means is that the amplitude equals 3. Now, that gives us an equation, S of t equals negative 3, because that's the initial value that we just described at t equals 0. And then cosine, well, now we have to figure out omega, and the way we do that is we were told that the period was 8/10 of a second. And remember that the period is defined to be 2 pi over omega. So that what we do is solve this equation, 2 pi over omega equals 8/10. What that means is that omega will equal 2.5 pi. So now our equation, plugging it back in, would be cosine of 2.5 pi times t. So that's the equation that describes this particular motion in this example. We were asked to find S of 1, in other words, when t was equal to 1. So we plug 1 in for t. So S of 1 is going to be equal to negative 3 cosine 2.5 pi times 1. When we calculate all of that out, we end up with S of 1 equaling negative 3 times cosine of 2.5 pi, and from the calculator, cosine of 2.5 pi is equal to 0. So S of 1 would be negative 3 times 0, which is 0. What that means is that the weight is at equilibrium when S of 1, or in other words, t equals 1. So therefore, if it's at equilibrium, it's neither moving upward or downward. All right, often we are given an equation which describes simple harmonic motion, and we are asked to analyze the motion. Here's an example of simple harmonic motion for us to analyze. The position of a weight attached to a spring is S of t equals negative 4 cosine 10t inches after t seconds. A, what is the maximum height that the weight rises above the equilibrium position? B, what are the frequency and period of the function? C, when does the weight first reach its maximum height? And D, calculate and interpret S of 1.466. The motion is harmonic because the model that we were given is of the form S of t equals A cosine omega t. Since A is the amplitude, and the equation we have is S of t equals negative 4 cosine 10t, we know then that the weight oscillates 4 inches below its equilibrium and up to 4 inches above its equilibrium, which is to say that the amplitude equals 4. All right. The period is 2 pi over omega. And of course, omega is equal to 10. So this is 2 pi over 10, which equals pi over 5. Now, the frequency is simply the reciprocal of the period. So that's 5 over pi. The next part we were asked to find is the time in seconds to complete one full cycle, which is, of course, the period, pi over 5, that's equal to 0.6283. Now, 1/2 of that is the time that it would take for the weight to reach its maximum. In other words, we need 1/2 times pi over 5, which is pi over 10. So it would reach its maximum value in pi over 10 seconds. The last part was to find S of 1.466, which means we plug this 1.466 in for t, representing, of course, the time in seconds. So this would be -4 cosine 10 times 1.466. And when you evaluate that, you'll find that S of 1.466 is equal to 1.9973. And what that's telling us then is that after a time of 1.466 seconds, that it's at approximately 2 inches above equilibrium. Let's go to the calculator, plug in this equation, and graph the equation to see what it looks like. So on our on our calculator, we plug in for the y key -4 cosine 10x. Then for the window, I've plugged in 0 to 2 and -5 to 5. I hit my graph key and it graphs that particular equation for us. The equilibrium point is, of course, the x-axis. So you can see that it goes up to amplitude of 4 and down to -4. So it's oscillating between 4 and -4. Now, in terms of that time, 1.466 seconds, I just want to point out that in that amount of time, this graph would complete 2 1/3 cycles. And we could find that by dividing the time 1.466 by that period, which we found earlier, pi over 5, which is 0.6283. All right, now it's your turn to solve a simple harmonic motion problem on your own. A weight attached to a spring is pulled down 2 inches below the equilibrium position. Assuming the period is 1/3 second, find a trigonometric model that gives the position of the weight at time t seconds. And part B, what is the frequency of this particular equation? Pause the video while you work on this problem, and when you're finished, restart the video to check your solution. All right, welcome back. Let's find out how you did. When the object is released, that means t is equal to 0. The distance of the object from its equilibrium position is 2 inches below equilibrium. If S of t is to model that motion, then what we know is S of 0 must equal -2. So then, that means S of t equals -2 times cosine omega t. So how do I know to choose cosine as opposed to sine? And the reason is, we know that when t is equal to 0, that would make omega times 0, 0. Cosine of 0 is 1. And therefore, -2 times 1 gives me my -2. So that's why we choose cosine. Now, what about finding the value of omega, which in this case, remember, omega is that angular velocity that we talked about. We do that because we can find and solve omega using the period. Well, we were given that the period was 1/3. So what we know is that the period 1/3 has to equal 2 pi over omega. I solve for omega, and of course I get 6 pi. The trigonometric model of this motion then becomes S of t equals -2 cosine of 6 pi t. Remember that the frequency is the reciprocal of the period, so the frequency in this particular case is the reciprocal of 1/3, so the frequency is 3. Let's again graph the function and take a look at that on the graphing calculator. After hitting the Y key, enter -2 cosine 6 pi over x. The window I want you to set up as -0.5 to 0.5 for the x's and -3 to 3 for the y's, and then hit your graph key, and here you'll see the graph for -2 cosine 6 pi over t. All right, great job in today's lesson. A lot of good work. Now, in this section, we've briefly touched on simple harmonic motion. Models of radio waves, television waves, even microwave ovens are just a few examples of the many everyday items you use whose technology is based on simple harmonic motion. To gain experience solving problems using trigonometric models, be sure to do the exercises that your teacher assigns, and we'll see you next time.